I was looking through my statics book and I was trying to find an interesting 3D equilibrium problem that wasn't your traditional three forces and 3D space because those problems take a really long time to go through. And I've already done an example on that. So the one problem I found that I thought was interesting was this problem where this weight is held in equilibrium by three forces. Two of these forces are spring forces, and one force is a cable in 3D space. And what we are asked to do is figure out how far each of these springs are stretched, and we're told what the spring constant is. We're told that the spring constant K for both AO and OB is equal to 300 Newton meters. So all of these values right here are in meters. So it's 6 meters, 4 meters, 12 meters, and this is 20 kilograms. Now, how do you go about a problem like this? We're going to follow the exact same steps. We're going to draw a free body diagram that indicates all our forces. Then we're going to make sure all of our forces are expressed as Cartesian vectors. And after we have them as Cartesian vectors, we are going to use our equations of equilibrium. But when we figure out the force about this spring in this spring, we're not done. So the force of a spring, F of S, is equal to K times, we'll call it S or X. I don't want to use X because I don't want to get confused with the X-axis. It has nothing to do with the X-axis. So I'll use S. And what S is S is the distance that that spring has been stretched or compressed. In our case, we're looking at how far it has been stretched. So if we know our force, we know this K value right here, we'll be able to solve for this stretched length. So let's start this. Let's draw the free body diagram. On this free body diagram, what do we have? Well, first, I'm going to draw point O, and I'm going to draw the weight of this 20 kilogram weight. So my weight is 20 times 9.81. And this 20 times 9.81 is equal to 196.2 newtons. Okay, so what else do I have? I have this red line from O to C, and this is a force along a line. So we know this force is going to follow this line. So we'll call this some force OC. We also have this spring force. Now, these spring forces, you have to think about them a little way to figure out where your spring is. Is your spring going this way or is your spring force going this way? Well, if our spring is being stretched, it's going to get pulled this way, and that means it's going to exert a force. A spring always exerts a force that wants to bring it back to its unstretched position. So if we're pulling it to this positive y, it's going to exert a force back to us along the negative y. So this force right here, and I'll call this AO, is in the negative y direction. The same logic applies for this. We're pulling it with a force because this weight is pulling it towards it. So we're stretching it in the positive x direction. It's going to pull back, and it's going to pull back in this negative x direction. So this is going to go this way, and we're going to have some F, O, B. And now we have our free body diagram, and I'll just put in some lines real quick just to help with our directions. We need to express each of these vectors as a Cartesian vector. And we're going to start with the easy ones. So the easy ones are going to be everything that's the weight, FAO, and FOB, because these are along one direction. So that's easy. That's what we want to see. We say our weight is equal to 196.2. It's pointing in this minus z direction. So if this is z, this is x, and this is y, it's pointing along this minus z direction. So it's minus 196.2, and it's a k vector. Okay, let's look at FAO. FAO is pointing in the negative y direction. So FAO is equal to minus FAO, and we have a j component. FOB, FOB is equal to minus FOB, and it's in the minus x direction, so it's going to be an I component. Now we have to deal with FOC. And FOC isn't hard, but it's just a line in 3D space. A line in 3D space is force along a line. So the magnitude of our vector, f, along a line is equal to the magnitude of f times a position vector over the magnitude of a position vector. And how do we find the position vector? We need to look at both points of this vector right here. So we know it starts at point O and it points to point C. So if we subtract point C from point O, because we always subtract the head from the tail, we're going to figure out the direction that this vector is pointing in. So let's write down our position of A. So not A, O. O is at the origin, so it's 0, 0, 0. Or C, I don't know why I keep wanting to write A, but C, we have to go 6 in the X, we have to go 4 in the Y, we have to go 12 in the C. So C is going to have 6, 4, 12. All right, so the magnitude of this is going to be FOC, and I'm going to do this in line, times, well, now we have 6 minus 0, so 6i. Then we have 4 minus 0 plus 4j. Then we have 12 minus 0 plus 12k. And what's the magnitude of this? Well, this is going to be the square root of 6 squared plus 4 squared plus 12 squared, 144, 160, 196. So this is going to be equal to 14. So this is going to be divided by 14. And let's figure out what this is. 6 divided by 14, 4 divided by 14, and 12 divided by 14. So our force along the x is going to be equal to 0.429 FOCI plus 0.285 FOCJ plus 0.857 FOCK. And actually, let me make sure I'm just rounding consistently. This I'm going to round up to a 6. So now all of our forces are expressed as Cartesian vectors. We can use our equations of equilibrium. Our equations of equilibrium are the sum of the forces in the x are equal to 0. Now anything with an I component, we have minus FOB plus 0.429 FOC is equal to 0. In the y direction, we have the sum of the forces in the y are equal to 0. So we have minus FAO plus 0.286 FOC is equal to 0. And in the z direction, now we're actually going to be able to solve for something. So the sum of the forces in the z are equal to 0. We're going to have minus 196.2 plus 0.857 FOC is equal to 0. We solve for FOC. So we're going to bring 196 to the other side of the equation, so it becomes positive. And we're going to divide by 0.857, and this becomes 228.9. So FOC is 228.9 newtons. Now we can back substitute it into the sum of the forces in the x and the sum of the forces in the y. When we do that, okay, FOB goes to the other side of the equation. And this is equal to 0.429 times 228.9. And this is equal to 98.2. And I want to remember this, so let me star this. And same thing for some of the forces in the y. FAO is equal to 0.286 times 228.9. And this is equal to 65.5. And let me star this as well. So we know what the forces along the springs are, but now we can use this equation and we can figure out how far this spring has been, in this case, stretched. So let's do that. Let's say, all right, for FOB, I can have the force of my spring, FOB, is going to be equal to my spring constant times how far this has been stretched. And this is going to be 98.2 is equal to 300. We know what that spring constant is. It was given times this, how far this spring OB has been stretched. So we're going to divide 98.2 by 300. We get this is 0.327 millimeters, or meters. This could also be equal to 327 millimeters. And we do the same thing with our other force. So here we have FAO is equal to K times SAO. This is 65.5, which is equal to 300 times SAO. And SAO is equal to 65.5 divided by 300. And we get this is 218 meters. Or you could say this is 218 millimeters. So let me write this. This SOB is equal to that. So hopefully this helped with a 3D equilibrium problem. A little bit more interesting than some of the other problems, most of the problems that you see with 3D equilibrium, where all three of the members are in 3D space and you have to solve for each of the tensions. In this problem, we were just trying to solve for how far these springs had been stretched in order to keep this system in equilibrium. If this video helped you and you liked it, please like the video. Please subscribe to my channel. It helps my channel grow. It helps these videos find more people. And until my next video.